future, both on the FCC, the networks that we have, the operators, uh, the consumers and industry. So a fairly far-reaching set of studies. Uh, the actual study can be found on the FCC website under the Technological Advisory Council. What I'm going to do today is do a very brief introduction, and then I'm going to ask each of the panelists to go through a few view graphs. I hope we each take around 5-6 minutes apiece, and then we will start the panel discussion. So to lead all of this off, let me move to the first view graph. And, if I listen to the talks during the day, I think it started off with Tom Bradich actually talking about this. When you look at IoT, you can think of it as a control loop. It has a purpose. You sense something, you aggregate data, you extract information, you model the situation, make a decision, and take action. If you're in an enterprise space that does a lot of different activities, you probably have tens of thousands of loops of this kind going at the same time. So the larger problem is, how do you actually do this efficiently? How do you coordinate and orchestrate what's going on? And how do you make better decisions? Because that's where the value is. So that's one of the points I wanted to make in terms of thinking about what IoT is all about. The second thing, and a lot of folks discussed this today, is really this convergence of information and communication technologies and operational technologies at the same time. And it's taking various forms of access, not just 5G, merging it with computing, storage, sensing, and closing that loop with actuation. Much more complex than what we've done in the past. And this kind of convergence is not just about technology, it's also in the sociology of how we work, how organizations are put together, and how we work within a larger ecosystem. The next item is when you look at this convergence, and I think we've been again talking about this all during the day, is what's the nature of our networks? What timescales do things really work on? So from real time to a much slower time scale in which we make decisions, to things that we might do in the cloud if we're using AI, which is things like deep learning. Lots of different edges in this, but it's a hierarchy. And it's a hierarchy that has three things built into it minimally: the computation, communications, and storage. When you actually put the various platforms folks have talked about, you have that control loop at the bottom. The next is when you look at AI and ML processes, and we'll be talking about this, I think, in each of the individual presentations. Again, it's a time scale that happens from real time to things that are intermediate, to things that may be in the cloud that are quite slow. It requires all kinds of resources, lots of feedback loops. And each of those feedback loops, in fact, means that you have to have connectivity. If you have many, many different independent AI systems going at the same time throughout an enterprise, it's very complex patterns. And it's not just communications, it's also access to the rest of the infrastructure. And then I would say, an important consideration in all of this, because I think it'll feed into the upcoming discussion, okay, and that is when you start looking at the statistics of how many connected devices we have today. I think the latest report for this year was roughly 30 million connected devices. they're not all IoT devices. But if you were to look at sort of the watershed year, probably last year sometime, where the traffic is actually is dominated by machine-to-machine connections. And the biggest uptake is in industry, not in the consumer space, which really drove, I'd say, a lot of our industries as providers over the last 2 decades. So I think with that, what I'd like to do is, as a setting, is introduce Anne. Anne, I'm happy to advance the view graphs, but if you could just walk through your slides and start off with a brief introduction of your background, okay?
Okay, sure. Thank you, Adam. So my name is Anne Lee. I'm a CTO partner in Nokia Bell Labs in the Technology Strategy and Architecture group. We look at future technologies and we evaluate how they can be incorporated into our products and solutions. Next slide. It's a very brief introduction. Okay, so what I want to do is talk a little bit about what I call the Schrodinger's cat of big data and ML. And I know that this is slightly imperfect analogy, but I think you'll get the idea. So we know that machine learning has become possible these last few years based on a number of things. One of them is the availability of data. And big data has been something that's been talked about for a few years now. In fact, at the beginning of 2020, the World Economic Forum mentioned that the number of bytes in the world today is 40 times bigger than the number of stars in the observable universe at 44 bytes. That's 1 billion terabytes. For those of you who have terabyte hard drives, you get some idea with that as background information. By 2025, they're predicting that the amount of data that will be generated each day is going to reach 175 zettabytes globally. So that's a huge amount of data. Now, at the same time that we've got all of this data that's coming in that you would imagine would be a big bonus to machine learning, a lot of the data is actually inaccessible for model training. And that's because much of this data is in the hands of private individuals or private groups. WEF says that by 2025, 80% of this data worldwide is in the hands of enterprises or people. And even though by 2023, there's going to be about 30 billion IoTs in the world, and they're going to be generating a lot of data. The question is, who owns that data, and will they be willing to share that data with people who are creating AI/ML models? The data could be owned by the consumer, who the data is actually about. They're the ones that own the device. Or the data could be owned by the service provider that is offering the service through the device. Or if the service provider and the vendor of the device are two different entities, maybe the data is owned by the device vendor. So there's questions, there's at least two major issues with regards to sharing data. One is privacy, and the other has to do with whether the, well, we can go on to the next slide. Sorry, I'll get back to that. Anyways, so what's enabling the IoT explosion? The IoT explosion is enabled by 5G. It's really wireless connectivity that's making it possible to connect these devices. And 5G was explicitly specified to support low latency, massive connectivity for the Internet of Everything. 5G providing this IoT explosion is just one step. The technology is one step, but we also have to think about ethics. And ethics is important to the brand of a company, because if the company is not trustworthy, then people are not going to use your products. Ethics includes regulations, and regulations include privacy of the data that might be shared. And we're aware of HIPAA and GDPR as two very high profile regulations. There's also cybersecurity that needs to be dealt with, because now that you've got these IoTs all internet connected, hackers can get access to them, and you don't want, for example, a hacker to be controlling your car. And the data also that is being used to train the AI, we need to make sure that they're not corrupted, right? There's concern that the inferencing of the model could be brittle, so you might not get the right results. But there's also the possibility that the data that you use to train the AI model in the first place might be a problem, and it could be because you don't know whether the people who are labeling the data in the first place are doing it correctly, whether intentionally or not intentionally, or whether there are other reasons for the data to not be correct. And then there's fairness. We need to be concerned about fairness. Spectrum is, as we know, a resource that's very limited. And as we need more and more of that spectrum for this growth and explosion of IoTs, we need to be able to fairly share that spectrum between service providers as well as between users within the service provider, which is something that we do already today, but we're also going to be adding network slicing and 5G to do that even further. And of course, there's within AI, there will be use cases where we need to worry about moral dilemmas and who's responsible when a decision needs to be made that causes some serious result. Next slide. And then, sorry. The future, what comes next year and 10 years beyond next year? Well, there's work now being started in 6G. Yes, we're just starting to deploy 5G, but 6G, every generation of wireless happens in a 10-year cycle. And so it's time now to start working on 6G so that we can start deploying in 2030. And there's many initiatives around the world that have begun. What I'm showing here is an example of one. HexaX is an initiative that's being funded by the European Union. The effort is going to start on January 1st, 2021, so in a couple of weeks. And they're expecting that this will last 2.5 years, where participants will be defining the use cases that will blend the digital, physical, and human world together, as well as the categories of technologies that will be needed in order to support this blending of the worlds. This is going to include further increasing the capacity of the wireless system, providing even lower latency in the sub-milliseconds, maybe in the nanoseconds, even extreme reliability, maybe in the 99s, perhaps, and devices will, we hope they will be able to be zero energy devices, for example. And I have here a number of possible use cases that people are starting to explore as to whether they might be targets for 6G, including wearable devices, voice and gesture interfaces, context-aware devices and applications. Self-driving cars will finally become pervasive, as well as 24/7 health monitoring, and possibly holographic communications and dynamic digital twinning. And that's our vision for the future.
Thank you, Anne. Okay, let's go on to Nagin next. Nagin, if you say a little bit about your background and then get into the presentation too. Okay.
Thanks, Adam. Can you hear me?
Yeah, and let me just add one thing. One of the things Nagin looked after during the FCC study is federal investments in AI and communications. So that's one of the topics that she'll be covering, okay?
Okay, yeah, so thanks, Adam. I'm Nagin Himayat, and I actually am a principal engineer in the Wireless System Research Lab at Intel, and I lead a group which is focused on distributed intelligence and over wireless edge networks. So that's basically the focus of my group, and these are some of the contributors who've contributed to this particular slide deck. So Adam, next slide, and then next slide.
Okay, that's the safe harbor slide. Let's go on. Good, okay.
So yeah, I guess this panel is about how AI can be applied to telecom networks as one of the topics. So I mean, this sort of picture or slide is really showing that, you know, all aspects of end-to-end communication networks are going to be impacted by AI. And so ranging from, you know, more intelligent platforms to more better air interfaces to, you know, better management of networks, as well as service delivery and subscriber management. And I know that, you know, other people are going to talk about that. So I'll go to the next slide. Next slide. So the other thing that is also important is how, as been pointed out, is that the devices that are connecting to networks, as well as, you know, the networks themselves are getting more powerful. So there is a possibility of, you know, changing the paradigm for how you derive AI models. So currently the paradigm is that, you know, all data gets collected and shipped to the cloud where it's analyzed and models get developed and so forth. But now what you want to do is, rather, because of these more powerful devices and lots of data that get collected, you want to take the compute and move it to the data where it is generated. So you want to look at more distributed methods, and that basically can address some of the privacy issues that were pointed out, as well as the cost of moving data around, which is quite significant. And the new paradigm could be that, you know, each device that collects the data learns from that data locally, but since you want to learn from the wisdom of what other people have learned, you want to collaborate quite extensively. And this collaboration could happen through a federation where a central coordinator helps you, or it could be just peer-to-peer. So this is something that would address to some part the issue of data privacy, because you don't no longer need to actually share the data around. So this shift, perhaps in this type of, you know, how AI models are developed, could help address some of these issues. So next slide. So yeah, Intel and is partnering with the National Science Foundation. I think Adam referred to that. And we are driving this research program, which we just kicked off, for machine learning for wireless networking system. And the goal is to really look at wireless specific issues when developing machine learning techniques. And our goal is to come up potentially with a new architecture and way of designing wireless networks through AI methods. And then in parallel, we're also trying to see how best to design networks such that the machine learning compute workloads could be better supported. So there are these three research directions that this program is focused on, which is, you know, how do I optimize wireless networks using AI techniques, ranging from, you know, physical layer all the way to end-to-end application, as well as network management. Spectrum management is one of the core things that I think was also highlighted, and how do you better utilize spectrum using AI techniques? And then finally, can I do better computation of AI models with distributed data sets while addressing some of the dynamics that occur in wireless edge networks? So next slide. So I think Adam asked us to say, you know, what's next. And I think this was highlighted in one of Adam's slides as well. And I think Anne pointed out too, as you go to this more sort of safety critical applications such as autonomous systems, the requirements on wireless networks keep growing. So some of the work that we've done with University of Pennsylvania is to emphasize that instead of designing, you know, autonomous systems and wireless networks independently as it's done today, you really need to move to a co-design philosophy where you are trying to co-design control and wireless together, and perhaps use AI techniques as a result. So this left figure is just showing that I have this control problem that I'm trying to sense a lot of information, transport it over wireless networks such that the controller can make decisions. And usually you get requirements of 10 to the minus 9 reliability to do this control loop with the sort of stability. And what we've shown is that if you are really control aware, in the sense I don't need to control this plant if it is already stable, so I can save some of these resources to do other things, and I can scale my system better, or actually I can improve my control performance. And what this figure is showing is that if you do it in this way, the learned resource allocation actually achieves the lowest cost, lowest control cost, and you don't need to know the model parameters as such. So reinforcement learning applied to this problem actually can help you learn without model knowledge. So that's one of the areas that I wanted to highlight. And then the second, the right figure really shows is the AI model that you want to choose should be more suited to the structure of the problem. So if you're looking at wireless networks, you can think of them as graph networks. And if you design your AI models which can take that structure into account, you can do better. And this example is showing graph neural networks being applied to the problem of wireless resource allocation in interference environment, which is sort of like this connectivity can be thought of as a graph. And what we've shown is you can outperform known heuristics, as well as you can generalize better, in the sense going from a smaller network to a larger network is much better with these type of structures. So going forward, we think these are the two sort of things, or at least design philosophies that we will carry over to 6G. So with that, I hand it back to I guess Sujatha or Adam.
Okay, so Sujatha, you're next. A little bit about yourself, and then the talk. Okay.
Sure. Thank you, Adam. Really happy to be here. I'm Sujatha Banerjee. I am at VMware Research, which is part of the office of the CTO there. And our goal is to advance the state-of-the-art transfer technology into VMware businesses, and also work very closely with academia and other government organizations such as the NSF in doing the advancement in science and technology. So next slide. So we've been going through this network evolution for quite a while, and my background, I did not mention, is in networking, and I have been looking at software-defined networking and network functions virtualization for the last several years. And as we see this network evolution, the goal has been to have increased automation, increased efficiency, make things easier to manage and control, and also serve the different use cases that keep showing up. So all the way from data center workloads, enterprise workloads, to service provider, carrier networks, all the way now to edge computing. And the way I view machine learning and artificial intelligence helping us get to that next stage of automation efficiency, things are really very complex, and can we learn the models of the complex systems that we are operating, and get and automatically adjust dynamically to whatever changes we see. Next click, Adam. And what we are seeing right now is, at least in the research world, a number of different components in the network that are getting augmented by ML techniques. Much of this work is happening today in sort of for specific functions. So whether it's video streaming or congestion control or link adaptation in wireless networks, we are seeing these components now, which we have had for a long time, getting augmented with ML and AI techniques. Next click. And so, using things like reinforcement learning based approaches, where you can see that the controller has now been replaced by a neural network, for example. And while there is tremendous sort of excitement and optimism in getting these things to work and really make a difference to how we manage, design, operate networks of the future, there are quite a few sort of issues that we need to still think through. And both Anne, Nagin, as well as Adam have already talked a little bit about this. How do these models of the different pieces interact with each other? So interacting control planes, for example. How do we make sure that the models that we have developed of these very complex systems are not biased, they are operating in a fair manner? And really importantly, how do we sort of have that transparency into how the models are working? Because the explainability and verification of these models is extremely important before you go off and deploy these into the real world. And then finally, the robustness, adversarial attacks, for example, on the models. And when something goes wrong, who is accountable? So how do we sort of tie all of these things together? And this is basically what I see as sort of future directions that really need to be solved before we see ML and AI being deployed ubiquitously in any domain, but certainly in telco networks. Can we go to the next slide? And so I wanted to spend a little bit of time on the data ecosystem, and the prior speakers have also spoken about it. And I'm showing you a figure on the left, which is from a paper written by Google engineers 5 years ago, I think. But I really like this graphic because it shows that when you try to build the ML system to help manage and control your domain problem a little bit better, the ML part of the whole ecosystem can be quite small. Data is paramount. You need basically good data. You need to be able to manage and continue to collect data, curating that data, labeling the data. A lot of the techniques that are being used are supervised techniques that require sort of good labeled data sets. And what I have at the top here is another cat, and that's basically a representation of the fact that labeling infrastructure data sets is quite a different task and requires different techniques. And so focusing in on those specific problems is of great importance. Privacy, security, who owns the data has already been talked about. There are different kinds of data, so multimodal, time series data, structured, unstructured, static, dynamic. All of these things need to be taken into consideration. And these are really hard problems. And then at the end of it, I just want to spend 30 seconds talking about the fact as to how are we building these models today. There aren't really that many great data sets out there. There is work going on in the Linux Foundation and other places where there is this effort to make it easier for operations infrastructure providers to be able to share their data. But right now, a lot of the work that's going on is getting data from what are known as digital twins or simulation or emulation environments. And this is actually pretty tricky because if your digital twin or your simulator is not really replicating your environment, you're not going to have very good training data. And if you do not have good data, you're not going to be able to have good inferences. And so this is actually the upfront work that needs to go into really building out a strong ML system. Next slide.
Let's see. Okay.
Thank you. And continuing on the data front, a lot of the data is born basically at the edge today with IoT and edge computing systems. A lot of the data, as Nagin mentioned, does not really leave the environment where it was born. It's local to that environment. And thinking about sort of what these edge infrastructures looks like, what we've classified or we've understood from looking at these systems is that these systems are multi-tenant, multi-stakeholder, multi-vendor, multiple applications run on them. And it's, and operating on multimodal data. And so a lot of the work that needs to be done is to be able to understand how do you build data-centric infrastructures. And towards this end, just like the Intel partnership with NSF, VMware also has an NSF partnership on looking at the edge computing data infrastructure. We started a couple of years ago, realizing how central data was to a lot of the applications that needed to run at the edge. And so we've basically been looking at with universities who have been funded under this program on what the system architecture issues are, what the programming paradigms are in terms of making sure that the computations run exactly, there's some of it might run at the edge, some of it might run in the edge infrastructure, connecting the sort of the device edge to all the way to the core data center and cloud infrastructure. And then security, privacy, and data sharing is paramount. And on the analytics side, there are a number of issues that need to be looked at. So for example, if you're not going to be training the data, you're not going to be transporting the data all the way back to the cloud, and you're going to be doing some of that training at the edge, there are some resource constraints to be looked at, distributed and federated learning techniques where you do not share the data, but you share model parameters, and how do you optimize the sharing of those model parameters, because even that can be pretty huge. And at the edge, we have a lot of cyber physical applications, which we really need to look at the safety of such issues, a safety of how your AI infrastructure is operating, whether it's doing it correctly or not. And so in the sense of looking at the future, for me, it is all of these things that need to come together. And some of it is in the front end of the ML system, especially with respect to the data aspects. So maybe I'll stop here and we can go to Q&A and discussion. Adam, back to you.
Okay. No, thank you all. So we have one question that's come in. It's from Sudha Jamte. And the question is learned resource allocation good for a cross-industry federated learning system?
Maybe I can try to answer. So, I mean, if these are currently still offline trained models, and if there are sort of vendors who are trying to train these models and would like to have access to other vendors' data, then this could be an application which could be federated and learned. So my answer would be why not? Yeah.
Yeah. In fact, looking at the question, I can think of the following. If you look at things that are cross industries, there are still horizontal goods that everybody uses. Everybody uses similar computers, let's say. If it's manufacturing, similar electrical motors, things of that sort. And so it makes sense to me that you would federate the data across industries to figure out which motors work better, which ones are more efficient, what are the telltale data that will tell you that they're going to fail? So the answer is yes. Okay. Yeah.
Thanks, Adam.
Okay. So I think Sudhata asked a little bit more, and that is she was thinking about federated learning for autonomous vehicles. Okay. So I don't know whether anybody has expertise on that use case or whether we should go on to the next question.
I mean, definitely, this could be an application area where especially if robots are, collecting data and they can do some computation, and you might be able to train them in not maybe in a federated way, but even in a decentralized way. So definitely, this is of interest. Now, the question is whether privacy is an issue in some of these cases. That is to be looked at. But even if privacy is not an issue, some of these data sets are very, very, you're continuously collecting videos and so forth. So it still makes sense to do some computation locally before you, and share the models as opposed to the data itself. But this is something, this is a trade-off that needs to be analyzed.
Yeah. Okay, so the next question is from Leonard Lee. And the question is, what kind of challenges do you see? Fragmented readiness and maturity of infrastructure technology of operators imposing on the realization of these autonomous network infrastructures. Do you see a need for tiered and segmented architectures for intelligent networks? Or do you see sort of bits and pieces that fit somewhere? If I were to look at a 7-layer model, does each layer get its own approach, or is this all federated in some ways?
So I can take a quick crack at that. This is a really great problem. And I mean, this is a really challenging problem, as you say, Leonard. You have to start somewhere. And I think what's happened is that we are starting at, looking at different, say, layers separately. But somewhere, when you start deploying these separate model-based, ML augmented systems, they will need to interact with each other. And that part, I think, is not quite there yet. And definitely a lot more work needs to be done. So I don't have a very satisfying answer, perhaps, saying that this is solved in this one particular way or another. But I think that you have to start somewhere. And so starting, with sub-functions of the network infrastructure is probably the right way to go.
Yeah.
I don't know if...
Sujata and Anne, for both of you, and maybe Nagin, if I look at it historically, in the world of long ago, when we had switching systems, AT&T, Western Electric used to build what were called class 4 and class 5 switches. Mm-hmm. And those were really pretty autonomic. Okay. They sort of ran the network. Okay. And
they still exist too.
They do, and they are all
yes.
AI-based essentially, even though they were put together a long time ago. Okay. And what I would claim, and I'm just curious what the reaction is. I think with the way we're building networks, we haven't even come up to the level of what some of the switches were capable of.
That to a certain extent, you're probably correct, because even the 4ESS switches, for example, they're still alive. These toe switches. So. Yeah. But I agree with Sujata that in order for us to be practical about implementing these AI capabilities, we have to start somewhere, and in order for us to make progress moving forward, probably you'll have to start in a very focused manner, and as independently as is possible, because we don't yet have the ability to coordinate across, when we talk about AI and we especially think about reinforcement learning, for instance, that was talked about earlier, eventually we will need to be able to coordinate multi-agents across the networks, because some of those agents might be at cross purposes too. There might be some agents that are trying to, maximize the quality of the service, and another that might be trying to minimize the energy that you're using, or something like that. That might, be at cross purposes sometimes, and you have to do coordination across them. And if you are in a multi-vendor scenario, then you have, and even, I mean, it's hard enough to do it within your own system to do the multi-agent coordination across multiple nodes or multiple functions within a node. But to now have to do it across vendors, we would have to do some work in standards to be able to enable that. So there are challenges, not that you couldn't do something today with AI for specific, maybe a little bit more narrowly focused purposes. Goals.
So we're actually, believe it or not, near the top of the hour. So let me just ask maybe a couple of questions. It might be useful to say a little bit for the audience, being on the research side of things. When you look at application of AI to specific problems, we have seen that, let's say, facial recognition, looking at extracting things from photographs, it's working fairly well. When you start looking at the kind of problems we face in networks, okay, how well do we actually understand the level of maturity and the size of the problem that we're facing, okay, and whether the AI techniques are stable enough at this point and whether we can trust the results well enough?
These are early days.
Okay.
So I think we'll get there, but it's sort of at the stage where you have to come up with domain-specific techniques as well. And so this is to Nagin's point about using structure that you know exists. And I think having sort of one technique work across all domains is clearly not possible. And so that's basically where we are, I think. We are taking existing techniques and now applying them for our specific use cases. And even within the network stack, different kinds of functions will require different kinds of models. So that's work in progress. I don't know if Nagin has more to say here.
Yeah, I think we've discussed this amongst us quite a bit, right? In the sense that currently, especially if you have live, networks and so forth, where you're trying to deploy these solutions, there needs to be a safety valve, and a lot of people have commented on the brittleness or unpredictability in some cases. So having some kind of scheme, at least in the near term, where the AI system recommends something and then the human being can check that result and act appropriately is what would be needed in the near term until things get a better handle on that.
So let me ask one other question again for the benefit of our audience. If you look at radio engineering, understanding of electromagnetics, we had analytical techniques that took us to a point. I think with the power of computers, we have learned to do quite a bit of simulation work on networks, okay? What do you see as the qualitative difference, okay, in terms of advancement by going to these machine learning techniques, okay, that the science, seems to have sort of hit a brick wall almost, okay? Are we are we hoping we'll be at the next level with this? What do you see as the contrast?
I can venture something, and then maybe others can, add to it. Definitely, I mean, there are areas, as even in the ML-WINS program that I pointed out, that there are areas in wireless networks that are well modeled and well understood, and part of the research is just to see whether the techniques that are developed by AI actually can reproduce these results, which are well known reliably. But there are other areas where the complexity of, as I think people have commented on, the number of bands that you have to support, and the number of ultra densification in the network, and the type of services and the safety criticality of some of these services. It's just not possible to design, or there is no model-based approaches that work there. So even though some, I think Sujata pointed out that some combination of domain knowledge and understanding needs to be applied, but the fact that currently these are not solvable by domain, model-based solutions require some new tools, and a data-driven techniques at least, has some promise to solve some of these things. So I don't know, maybe Sujata and Anne can comment here.
Yes, I think some of the algorithms are very well developed today, but we're still exploring to see whether there's some value we can gain by doing it a different way with AI/ML, for instance. Having some AI models, maybe it could save on costs, for instance. Or in some cases, though, being able to more dynamically and in real time adjust to conditions in wireless, especially, that changes more. You can just see the future where you might be able to do this with this technology, right? You see the potential. It's not quite there yet, but you see the potential, and it's like it's sort of within grasp if we keep working. If we work hard enough, we can get there.
Okay.
So yeah.
So I have one last question. It's actually a good one, and I'm not quite sure who asked it. Is there a recommended starting point? Maybe security, maybe network anomaly detection, maybe intelligent failover or offloads, things of that sort, okay? And what I want to add to that is, it might be good to have all of you answer it, but it might be good to interject. What AI things do you already see the operators using, okay, where there is some success? Okay. And maybe let me start at the tail end. Sujata, you first.
Sure. So all of these, so security is a big one. Network anomaly detection, I think, is another one. Capacity planning, prediction problems of all sorts, right? Workload prediction. So I think, I don't know if there's a starting point, or we do all of these in parallel, trying to understand each of these sort of subsystems and problem goals, and trying to come up with solutions. But certainly security, anomaly detection of all kinds, and sort of just capacity planning or prediction problems, I'm seeing quite a few.
Okay. What about customer experience problems, more on sort of the softer side of the business in some ways?
Oh, absolutely. So I think, things like chatbots, for example, where you're trying to automate some of the interactions with customers, or sort of trying to debug problems. I think there's work in that as well. And again, the extent of success, I think, varies depending on your specific problem. But certainly that, I think the softer side, as you call it, is also seeing quite a lot of traction in terms of a nice problem space to apply machine learning to.
Okay. Nagin?
You're on mute, Nagin.
On mute. I'm on mute, yeah. So yeah, I echo what Sujata is saying. And I wanted to mention that I listened to a talk by a Verizon expert who sort of mentioned that previously, they would have their own experts who would kind of tune the network in a certain way, and all the AI techniques could never beat their actual human experts. But recently they started seeing some areas where, the AI techniques actually beat their experts. So she was pretty hopeful. So I think there is some benefit of going in this direction. So that's all I have.
Okay, so Anne, we're going to give you the last word. Okay.
Okay, so I agree with Sujata and Nagin. I think near-term operations is an area when there's a fault. How do you find the root cause for it? It's rather challenging. You have to narrow it down. The tier one engineers have to narrow it down from this huge system to exactly which node is it coming from, and then you need to ultimately figure out is there what is the problem? Is it that there's a hardware problem, or is there a bug in the software? Or these are not easy things to solve. And so if we could automate this is great. But even if we can provide more assistance with tools that are intelligent, that would speed up the time to resolution of these potential problems. No systems are ever perfect, and especially if you have a multi-vendor system too. That's huge across, if you have millions of base stations eventually, especially with these small cells, it becomes very challenging, very complex to find the root cause. So AI would be a great help in providing assistance.
All right. So I think with that, we could probably go on for a long time today. Okay. But with that, let me thank you for participating in this session. And I hope our audience found this interesting. So I think, Kevin, we're probably ready to move towards the wrap up.
Yes, we are. And first of all, I want to take the opportunity to thank the panelists for an absolutely blow-away session, really on the money, especially when it comes to things like ethics and, the connectivity, bottlenecks. Where do you begin? As you said, Doctor, you could have spent a whole day on this topic, but somehow we managed to cram it into an hour. So kudos to each and every one of you. Thank you very much for being a part of this. You're very welcome to stay and be part of our wrap-up, ladies, if you like, or you can sign off. It's entirely up to you. But certainly, we're going to spend a few minutes here, Dr. Adam and I, just kind of going through the last rites of the IoT Grand Slam 2020, and what a 13th event it has been for the IoT community. Lucky for some, perhaps not for some others. Let's put it like that. For some reasons, which we won't go into on this particular part of the close, but I'm glad to say that we had a very stable and consistent flow of folks participating through the whole day. And I'm going to just bring this one screen up to hopefully reflect. Hopefully you can see that, Dr. Adam.
Yep, definitely.
Okay, so that is our closing slide for the wrap up, and it just reiterates the fact that we're very grateful for each and every one of you attending our IoT Grand Slam. And you heard it here first. We're going again for our 14th IoT Slam branded event, which will be taking place April 9th, 2021. That will be a virtual only program, and we will be going from that into our live Slam program with Dr. Adam Drobot and the IEEE, June 20 to the 24th. So between June and now, we obviously have this April 9th event to look forward to. So, Doctor, maybe you can kick us off with the closing summary and the remarks from how you saw things during the course of the day.
Yeah, so I think I took notes during the day, and there's very definitely a pattern in what we experienced. And I got to say, it was actually terrific in a number of ways. So before talking about the various presentations, there has really been a very strong progression, I think, from the earlier slams, where people were talking about what they might do. I think last year it was about actually talking about deployment as opposed to POCs. And I thought what was absolutely terrific about today, it was sharing experiences from actual deployments in a very honest way, saying what worked, what didn't work. And I got to say, it's very gratifying to see that kind of progression. Okay. that's what this whole community is all about, is to share those experiences and figure out how we all improve and move forward. So if I then look at sort of large scale themes that came through today, even though we had one specific presentation on it, a lot of folks talked about digital transformation, bringing together the ITC world, information and communication, sorry, ICT world, information and communication technology, together with operational technologies. A very mature discussion because it dealt with the underlying technologies. It dealt with the organizational structures and mindsets that people have, dealt with the need for education, and it dealt with the changeover in business models that would result from that. And I got to say, quite a few of the presentations actually hit aspects of this. So that was a very, very big theme. The next one that came through was the edge. I think, as Dr. Tom said, anything that's not in the cloud. I think we heard everything from the tiny edge to almost in the cloud, and the value that comes from doing that. A lot of discussion this time about, I would say, techniques of how you actually build solutions. Why you might use Agile for something, why you might use a particular process for something. All of that came through. And then lastly, I have to say it's a little bit of a puzzle for me, but not that much of a puzzle. If you look at reports from analysts, they tell you what areas IoT is probably has the biggest uptake. If I were to list the use cases that our presenters went through, and I sort of think of economic classifications for the various verticals, I would say the group today touched almost every vertical, from things that government does at a federal level, defense, all the way down to cities and local activities, manufacturing. And again, when somebody says manufacturing, it's not just one sector. There are many subsectors in it. We heard from a lot of those things at the consumer level, all the way down to things like Raspberry devices that the makers are using. So again, really exposing the breadth of what was out there. So if I were now to turn to sort of the actual presentations, I think Kevin started off the day with opening remarks, went through all of the things that are happening within the IoT community, from the centers of excellence to the events that are being held. I thought that was terrific. And then we had the first the opening talk. It was Dr. Tom, and I'd say it brought yet another dimension to these events because he dragged in 3 sets of customers. So it's not just the solution providers who are talking, but you had the voice of the customer as part of this. The next talk was the Diamond Panel. Again, I have to say a terrific set of discussion because it really talked about service as a model, using IoT as with a service model. It brought up the real difficulty of operating in real-time environments, and again, exposed that stress between the OT and the IT world, I thought in a very constructive way. The next one was OT-IT convergence. I think I've already said quite a bit about that. Digital transformation, the application of IoT in manufacturing, again, a very informative one because it is one of the big sectors where there is a take-up. And if you look at the data from the analysts, it really seems to be probably the place of most influence right now. A fantastic talk on the COVID response in the keynote talk. And again, just sort of reflecting on things, you could say, where would we be if the kind of technologies we're talking about were not available to us just to get through this COVID epidemic? So I think that was there. The Journey by Rheem on their connected water heater. Again, a very practical application. We have those all over the place. And again, I think the value of having a slam like this, having somebody share their experience, what went well, what didn't go well, I think is invaluable. The next one was the panel on women in IoT. And again, what I have to say is the level of honesty of sharing all the trials and tribulations, looking at where there are bright spots, very, very fantastic discussion. From my own experience, when I was an undergraduate in engineering, we had a class of 711 people, and of those, 8 were women, okay? So no feed stream almost. I have to say I'm actually very proud of it. I went to Cornell as an undergraduate, and last year's class was actually slightly over 50% women, okay? Shows you great progress, but not enough still in the events that we're doing. And so I thought great discussion. Next one was development. How do you actually build things? Great discussion on agile methodologies. I have a feeling it's probably worthwhile concentrating more on that topic as to what else is there. Waterfalls have their problems. The more complex something is, the harder it is to build in the requirements late in the game. So cyclic development, agile, things of that sort, good exposure. Next panel was security and trust. And again, it's something that shows up on every customer's list, high up on their requirements for, why do I hesitate on doing IoT? Is it secure? Are the responsibilities in the right place? Do I trust things? Tend to be top of mind. I think Kerry Shih, the next talk, Tiny Edge. I think if you were to look at the academic world, probably a little bit beyond that, and that's smart dust. But it's amazing how you can make small things, cheap things that yet bring value. I think we've all been struggling with this. How do you get customers to go past the point of concept and get things done? And I would say, again, if you look at the literature, there was a McKinsey study. It says 70+% of all projects fail. I think for all of us in this industry, figuring out how we get to faster closure cycles and do substantive things that add value for the customer, very important. then the connected worker, and closing out with the panel that we just had, which is looking at some of the futuristic things that I think will lead to more automatic things and really automation on a big scale. And then the last word I would say is, as a community, what was really exposed is how do we deal with sort of the breadth of IoT and the complexity that it represents. So I thought a fantastic day, lots of topics, and I think really the highlight was the willingness of people to share their experiences, whether they were good or bad, because that's the only way we make progress. Okay, so I think that would be my summary for today, Kevin.
Oh, you couldn't have put it any better, Doctor. I can't thank you enough for taking the time out of your busy day as well to kind of sit through every one of those sessions. And it looks like, I'm looking at some of the folks that are still on the line here. I do recognize a few names that have been there with us from the start. You iron men and women, you. What can I say? Kudos to you for sitting through a whole 12-hour day, more or less. And I think as we reach the top of the hour here, pretty much midnight UK time, I want to just wrap up by saying a huge thank you again to everyone that has participated in making this, for me, the best IoT Slam yet of the 13. And so we look forward to hopefully welcoming you all back to the IoT Day Slam in 2021. And between now and then, look out for the on-demand content coming up in the next few days. So that's a wrap, folks. Thank you very much. God bless. Stay safe. We'll be in touch soon. All the best.
Thank
Cheers,
you,
Doctor.
Kevin, for putting this terrific event together.
Thank you. All the best. Take care.